We are going over two major things today. Just as a kind of a FYI. So last class we started talking about operator overloading, and today we're going to talk about overriding the specifically the output stream operator. And the input and output stream operators get overloaded a little bit differently than some of the other operators, because they are not applied to the class itself. So if we want to override like the addition operator, or we want to override the greater than Boolean test operator or something like that, those are applied to the class that we're running ourselves. The output stream goes to an output stream object, not our class itself. And so we have to be a little bit careful of that. We'll talk about how and why we're going to do that specifically in just a minute. And then we're going to look at the beginnings of the next topic, which is inheritance. Inheritance is going to be a huge way of how we're going to take a base class, and sometimes this is called a parent class, and we're going to derive a child class from it. We will finish that conversation on Thursday. It's probably too much information for one day, so that's how both of these are kind of big. That's why there's only two things we're covering today, and we're going to finish up the derived class on Thursday. So that's going to be a good thing. I'm hoping to get done a little bit early on Thursday. That way you'll have time to work on your final project, and you'll have a chance to work on next Monday. I believe we're having class as well. That is May the 4th. May the 4th is the last day of class for this term. That is going to be just kind of an open review and project work time. If you guys have questions, anything about that we've covered from our last test until, well, it's going to be Thursday. Anything you have questions about there, we can cover. Anything that we can do, if you have questions about the final project that's due, you can talk about that and get information there. So it's going to be kind of optional as far as that goes, but it's still kind of an important aspect. So do make sure that you come to that as well. I have not seen, at least not yet, any more information about if you guys have done the online course evaluations. If you haven't, I believe you have until Monday to do that. So please take a couple minutes to do that. Excuse me. I know school looks at those. I look at those. Anything we can do to kind of make those better. All right, so let's look at overriding the output stream operator and what that entails. Like I said, that is kind of a big thing. It's a little bit different than the other operator overloaders that we've looked at. And so we want to kind of look at those type of things. Now, a lot of languages out there, and C++ does not have this by default, but a lot of them, people will put in a special method called the toString method. And the toString method is designed for you to be able to easily call and say, hey, I've got an object, and this object could be a student, it could be a course, it could be a circle like what we've looked at. And I want to convert this to a string so that I can put it in some sort of output. And so a lot of times we'll use this toString method. Now, by default, because of the complexities that an object might have, if you call toString, it may not give you any relevant information. You know, you might get like a memory address or a class name, or maybe both. Kind of depending upon what programming language you're using is going to define what you're going to get. That's not real helpful. Not that it's a problem, it's just that's not real helpful. So in a lot of other languages, you'll have to do something called override this method. That way you can, work with it. At the same time, because it's not built into C++, you can make it whatever you want, but you've got to create it. Now, the alternative is to just override the output stream operator. So that way, anytime you're saying something like cout and a couple of less than symbols, you can drop your object in and it's going to add that to the stream and out you go. So that's kind of the in a lot of ways the goal of the toString operator, and we can do that in C++ just simply by overriding the output stream operator. Now, the biggest question we're going to have to ask ourselves whenever we do this is, what is it going to be that we want to print out? So, for example, if I had my circle class, just as an example, I had my circle class. We've been working with this for a couple weeks. We kind of, hopefully you're pretty familiar with it. You probably want to ask yourself, well, what about this makes it that I would want to share? Do I need to share the radius? Do I need to share the XY coordinate location that it's in? Do I need to share the area of the circle? All of the above? None of the above? Do I just need to say, you printed out a circle, what do you want? There's a lot of question that needs to be involved with that. Part of that's going to come down to how is this going to be used. So if I'm printing something out, for example, for an end user, that's going to be different than if I'm printing out to save the file to a server, or save this information to a file on a server, to transmit it across a network to another server, etc. Those operations are called a serialization, and serialization is just taking a complex data, breaking it into its primitive core components, and then sending it down some sort of stream. That stream can be streamed to a file, streamed to across a network. It can be a lot of different ways. So thinking about how we're going to use this and how this operator needs to be used will really define how we're going to override this. In another class that I teach, we talk about transferring data between systems that are not the same. And so one of the things we look at is doing things, for example, like same as an XML file or as a JSON file. And so one of the things that we've got to think about as well, if I'm going to send this maybe to save on a computer as a computer file, then maybe I need to kind of prep it for that type of work. And that's fine. You just have to kind of know what it is that you're doing. Now, as I mentioned, because our operation is not actually part of our circle class, is actually part of the output stream class, we need to do something special called create a friend function. Now, a friend function is talked about inside the book, and you can read a lot more in detail with it there. But our friend function is simply going to take a method, and you can see example here on the screen. You're going to put friend in front of it, and this operation is going to belong to a completely different object, and that's fine. But what we're saying is, if I put this inside of my object, I'm saying this method is a friend of mine. Because it's a friend, I am establishing a trust relationship with it. Now you might go, well, what type of trust relationship? Well, if you remember, when we define a class, we have private methods and we have public methods. Let me pull up C++. Here's my circle.h. Here, as you can see, we've defined these public, and here's these methods here, and a couple of, and a static object, or excuse me, a static property. And then down here, we have private properties. Private properties by default cannot be seen outside of our object unless we use this friend keyword. The fring keyword goes before everything else and says this because I'm trusting this, and I know there's a trust relationship because I'm putting it inside my class definition. So I'm saying I trust this. I am going to allow to have access to these private properties. That's all it means. Okay, so you'll notice with the output operator, we specify a return object type of OStream. We have our operator angle bracket for less than. We have an output stream as a parameter that gets passed in called out. And we're passing in a circle ourselves. Okay, so all pretty straightforward as far as that goes. Now, with this, if I come into my circle, now everything else inside my circle is staying the same. I'm not having any changes there, not until I get all the way down here to my output operator. This is where I put this in, is in my circle.cpp, but notice that it does not have the circle and the 2 colons in front of it. It's because it does not belong to circle, okay? The other thing you're gonna notice that's a little bit different is I did not put friend in front of this, not necessary, okay? Now, this OStream or output stream object that's gonna return is what allows us to string multiple objects one after another. So for example, and if I look at this, I have out and I have my output operator. Now this is a string that's getting passed into it. Well, I've also got something down here. How does that get applied to this? Well, what's basically happening is I'm being passed in my output stream. In this case, it's just the other output stream, OUT. It might be cout is what I'm using. It might be a file stream. It doesn't matter. Okay, those are all forms of output streams. It handles the first one, and then it comes back and adds this to the appending to the end. So it takes my string, and then that's returned. This becomes a new input and gets added to this output. So this allows us to do something called chaining our objects. Chaining is very important. We're going to see this more in other languages as you study. It's not as important in C++ as it is in some other languages. JavaScript uses chaining all the time. So does regular Java. C# does to a fair extent as well. So while it's not seen a whole lot here inside of C++, it is used in a lot of other languages, and that's just basically saying the output of one object can become the input of another object. And that allows us to chain, and instead of having to create a bunch of temporary variables, which takes time to create those variables, takes memory space to set them up, to reference them, to dereference them, all type of stuff, we simply go in and say, I'm going to chain them. And so once I create that temporary memory space, I'm going to use it and then use it and use it, and it gets allows us to use that information faster and more efficiently. That efficiency is going to be something that's going to come up, and we're going to talk about probably a little bit on Thursday. So kind of just keep that kind of in the back of your mind. Okay, so notice that this, however, inside of our body, notice that we have out. This is not cout. Usually we're used to writing cout. You so might go, okay, well, are you making a mistake? No. This out is a generic output stream here, this out. And the reason why we're using out instead of cout is we're going to return this object. We're not printing ourselves, we're returning it to another output stream to print to the appropriate place. So the appropriate place might be cout. And we'll see that in just a second. We're going to use that. It might be a file stream that's out. So if you remember, we've created some file streams as output operators way back, like week 4 or 5, something like that. So maybe that's where it's coming from. And there's other output stream operators that we haven't even seen yet. We're not going to look at really in this class, to be honest with you, but they do exist. And so it says, hey, I'm going to take whatever the output operator I'm using and allow it to be added to this. Now you might ask, and that's a legitimate question, why am I not using cout? In fact, if you look through all of our examples and all of our other methods that we've used in Circle, you'll notice that none of my methods inside the Circle object we've created or any other object we've created have used a cout function. And that's on purpose. Okay, that was not an accident. A object inside of C++ or any other object-oriented language needs to be about how am I storing information, how am I deriving new information from it, like for example, getting the diameter of a circle or getting the area of a circle. It needs to be about how can I manipulate that information. So I want to be able to set the radius, but I want to make sure that my radius is a positive number. Okay, those are things that my circle object is going to do and that I want it to do. What I don't want it to do is do anything that ties me to a specific component, for lack of a better term, of my computer program. So if I were to write, for example, a cout statement, a cout statement is very specific. I now have to write to a console, and I may not even have a console attached to this computer. Now you might go, how on earth would you not have a console attached to a computer? How do you know it's running? Well, a lot of server applications or a lot of system applications, they run behind the scenes. They don't have windows that pop up and tell us what they're doing. They just kind of run in the background. And C++, if you remember from earlier discussions in class, we've talked about how it's designed as was really initially designed to write system software. Is designed to be very fast, very efficient, and write that system software. So if we start trying to write something to a screen and there is no screen to write to because this is on some server way back somewhere, that could throw an error. And that's not good. We might have a system where there is a screen, but we're not using a console application. Give you a perfect example. I wrote an application fairly long ago now, several years ago, that it was kind of like an old-fashioned Etch-a-Sketch, and you could use. They had a couple of like little joysticks. It was kind of like an arcade game. You could use a couple of joysticks to move things around and draw objects on a screen. You had the ability to press buttons and draw certain shapes up on the screen instead of having to draw it using the joysticks and stuff. You could put pictures and shapes and stuff like that. So my circle object here might be very useful for that. I would need to know where is my X and Y coordinate for my location, how big my radius is going to be, so I would know how to draw it. Well, that's drawn very different than a cout statement. So just as another example of I might go send something to the screen, but it wouldn't necessarily work with a console type of application. So cout wouldn't be used. There was no console for that. It was all graphics environment. Another example is, like I mentioned earlier, if I'm going to save this information to a file, transfer it to another system. These are all real simple but real common examples of how I might take this circle class and use it in some other environment. This circle class can be part of a 2D sprite game. We talked about using collision detection. At least I talked to some of you about this in a game type environment. And so, if I'm doing a 2-dimensional game like the old-fashioned side scrollers, or a 3-dimensional game, I might extend this class into a spheroid. and make this, more useful for me. And that's an important thing to kind of keep in mind. So how I'm going to send information out, I always need to keep in mind, and I want that to be controlled by my main application. I want my classes to just store data and allow me to work with that data. If I need to print something out, I'll either create a special class for that, or that will be built into part of my application. Both are completely valid depending upon your application, how you're going to do it. And depending upon what your application is doing, we'll kind of decide which way that's going to go. You don't have to worry about that at this point. But you do need to realize and keep in mind that in none of these examples are we using something specific like writing to a file or a cout statement or something like that. And that is on purpose. So this out, standard out, is just short for our output stream. And that allows us to handle any type of output stream: networking, file, console, error, etc. Okay. In this case, I have written that, it's a circle with a radius of, and I specify the circle. Because this is a friend, I am able to directly access my radius. If I come back into my circle.h, you'll notice that radius by default is a private property. Private property, you're not supposed to be able to do it, but because we're a friend and we've defined ourselves as a friend, and notice that you have to be inside of your class to specify it's a friend object. I can't, if I was to go to my output stream operator, I can't say, oh, circle's a friend of mine, trust me, it's okay, give me access to his private properties. Doesn't work like that. The trust has to be established on who has the private properties and who am I going to allow to see them. Okay, not the other way around. And if you think about that, that makes like a lot of sense. A good way to think about this is if you're living in a house or apartment or something like that, you wouldn't want a random stranger to go up to your house and say, oh, I know Paolo, or I know Walter, I know Hunter, let me in. We're friends, it's okay. You don't want that. You don't want your, smart house to go, oh yeah, okay, well, you said you know them, so we'll trust you. Okay, that's because it could just be a weird stranger off the street, right? You don't want that. Instead, you want your smart house to say, well, if you want me to let you in, you need to prove that you're a friend, and not only that you're a friend, that they're trusting you. Okay, so how do you prove that? Well, I might give a key to the people who I want to have access to my house. And so that way, I don't have a smart house, I have a plain old house, but if you've got a key, you can put in the lock, open it up, and hopefully water my plants while I'm on vacation, or, to drop off my mail so it doesn't, pack up, stack up outside, or different things like that. These types of things, that you could work with. So that key that allows you to unlock that private residence is kind of like a physical representation to friend. Because I, as the owner to my house, have to give it to you. It's not like you can say, oh, I want this just to magically appear so I can get in. And that's how your friendship object works. And that's why we're allowed to access this private data. Okay. There are some rules about this, and you can read about it in a little bit more detail. Like I said, in the book, it is there. But this gives you a really good basic representation. And finally, notice, of course, that we return outs. So we took whatever our parameter out is, we made some modifications to it, and then we return out from there. So that's how it's working. It's very simple, very straightforward. If we weren't to return out, or we were to create a different output stream object, anything that was passed in prior to us would be lost. And that's kind of dangerous, you know, we don't want to lose data. So that's why we're going to keep this, we're going to keep this really simple. All right, before I move on any further, are there any other questions about overriding the output stream operator, anything like that? Okay. One other thing I do want to point out that is kind of important. Oops, wrong header file. This one. Oops. Don't ask me how that happened. That was wrong. That's right. Okay. So two other things I do need to point out real quick to you. Number one is we need to include IO stream, and this gets included inside of our circle.h file. The reason why we need to include IO stream is because of that output operator. If we were to delete the IO stream, notice that our O stream here is now a data type that C++ doesn't know about. Okay, so our header files can include references to other header files. That's an important thing to know. Because if we look at our circle.cpp file, you will notice that there is no reference to our IO stream. You might go, whoa, wait a second, what happened to it? How does circle.cpp know about OStream without having to use the include file? That's a really good question. And the answer comes down to the fact that circle.cpp includes circle.h, and circle.h has the include, so you don't have to include it multiple times. You just include it the one time. That's what this whole pragma once is about, is making sure that you don't accidentally re-include multiple files multiple times. And you see how easy it would be to do in a case like that. If I did include IOStream, it's not going to break anything, but it would work. Now, the other thing that you might notice, and just to point out, is IOStream is pretty common. In fact, if I look at my my intro to CPP file, notice it's here. You say, oh, but you're including circle. Well, yeah, I know I'm including circle, but I need to still be able to reference that file here. So that's just kind of where and how that works. The other thing that we have to do is we have to use namespace std. If you don't, your standard namespace is where OStream is specifically written. If not, you'd have to do something like std : OStream. If you take it out, notice that it also breaks it. So you need both of those values. Oops. There we go. Okay. And if I come over here to this, I'm going to call circle. And if I say something like cout C1 and del, and then I'm going to do it for C2 as well, just as a quick example. Compile this. You'll notice that instead of having to say something like C1 dot and some real big thing, because I did the override operator for my output stream, when I type in C1 into my cout, because I've overridden the output operator, I now can print something out. In this case, we are simply looking at the radius. I could have modified that cout statement to be something else, but I just want to go with something simple. Okay, so that is the other part of this that you do need to be aware of. All right. Let's look at base and derived classes. Now, this is something entirely different that we've not looked at before inside of C++. See, your book, I believe it's chapter, was it 14? Yeah, chapter, oh, no, 14 was the overriding. Chapter 15 is all about inheritance, and inheritance is the basis for base and derived classes. And you're going to find, if you're reading the book or if you go online and you look at people writing online tutorials or videos or stuff like that, you're going to find there's a couple of different names for the same terminology. So sometimes a base class will be called a parent class, and sometimes a derived class is called a child class. And the reason why is that you have a base class, something that kind of starts off, and then you can derive a brand new class from it. Now, because of inheritance, and inheritance is one of the 3 pillars to object-oriented programming. Because of inheritance, what it says is any child that's derived from a parent has all of the properties of the parent and may have additional properties. Now, you might say, well, does this kind of sounds like create an object from a class? That's not what this is talking about. This is talking about creating another class from a base class. So let's think about real quickly. I have, just based upon the things that we talked about before and in this circle that we've been working with, let's say I had a base class that I wanted to call my generic geometric object. Okay, a generic geometric, or maybe I call it GG for short or anything like that. If I think about all my different geometric shapes, there are certain things that are the same about all of my shapes. And let's go back to, I'm going to be building a drawing application so I can press a stamp button and boop, something will appear. It doesn't matter if I'm a triangle, square, rectangle, circle, any of those, your standard shapes. There's some properties that are going to be the same. Like, for example, I'm going to need to know what color my shape is. I might need to know if my shape is going to be filled or if it's an outline. I might need to know what my X and Y coordinates are so I know where to place it on the screen. I might need to know the size for this shape. All of those and the associated methods with them, all of those are very important to me because they help me define what my shape is going to look like. Now, a generic shape, I don't know what this is. And some things are going to be a little bit different. If I have a circle, it's going to be a little bit different than a square, which is going to be a little bit different than a rectangle. So I will create child classes off of my generic object that allow me to define things specifically to my type. So for example, if I have a generic shape, I might not be able to easily define what my area is. When I get to a circle though, oh, that's no problem. I know how to define that. If I'm a rectangle, I need to add an extra property. So I might need a size property to determine how big one side is, but another property to determine how big my other size is. So I can add both properties and methods to my child, or if you prefer, children classes, or in some parlance, derived classes. So this is the whole idea behind inheritance is I don't have to write those things that are the same. So I don't need to write my get X and get Y. I don't need to write the get color, get filled. That's done for me in my generic class. It's over there, it's done. I only need to write the things that are specific to me. So this simplifies a lot of information. The other thing that really makes this nice is that if I make an update to my generic geometric class, any changes I make there automatically get propagated down to my children. So I don't have to worry about, oh, now I have to go in and update all this stuff. Give you a perfect example. And, the way that this would work previously is, if we didn't have classes and didn't have inheritance and things like that, I might be tempted to go and do like a copy and paste. Well, a copy and paste isn't a bad step. It saves me a lot of time in writing. You've seen me do it a lot inside of different classes myself. Um, but if I copy from my parent class into my child class and I make an update, that update doesn't get re-examined, for lack of a better term. I've got to go in and recopy and paste that information. And that's a problem. Takes time. It's a good way for errors to creep in because let's say I've got 15 different derived classes and I remember doing 14 of them, but not the 15th one. Different things like that. All right, so let's look at what this is going to look like inside of the generic geometric instead of our header file. One of the things that you're going to notice is that because a base class needs to service additional potential objects, they tend to be a little bit more complete, as they're going to have a lot more to work with. And now I may not see the .cpp file for this if I'm not writing it. I don't need to. I just need my header file that I can include. And this tells me everything I need. So I've got my class. I've got my constructors. I have a bunch of different constructors depending upon what it is I'm building. I have some getters. I have some setters. That all makes sense to me. When I'm looking at them, I can kind of see how my getters and setters are going to work. I get a pretty good generic feeling for them. I can look at my private properties. This would be hidden from me if I was getting this externally, so I can't access it. If I had an API, this is what I would see, and that's fine. That's all I need. I could then take this and say, oh, I'm going to expand this into a user derived class. I'm going to make this a three-dimensional, be on a three-dimensional plane. So I'm going to add a z axis coordinate, or I'm going to, add a second size. And some of these properties up here might change because of that. That's okay. That's totally fine. Okay. If I were to look at my associated CPP file, it would look something like this. So here's just where I created my basic constructors. So I'm using this in my arrow in case it's an object. That's fine. Going through this whole process. And this is just, a real short snippet. If I come over here and look at this, you'll notice that I have in here the ability to get distance, get area, get size. I've done some other stuff. Get X and Y. Why do I need get X and Y? Because I use get X here and get Y here. Obviously makes sense. Notice that get area is the size times the size. That's not going to work for a circle. That's okay. When we look at this information on Thursday, we'll see how we can override an existing class, kind of like how we overrode operators and overrode other things. So it's all kind of building on each other. So I can just kind of start to see how this is going to build out. If I look at the header file, you'll notice there's a lot of different objects in here. There's a lot of methods I haven't written yet. It's not complete. So if I try to call get color, for example, because it's not there, it's going to have its own set of issues. That's okay. It's going to give me an error saying it can't find that symbol. I don't need to worry about that because I'm not calling it at this point. When I call it, I need to make sure, before I call it, I need to make sure that I write that. This is just kind of getting a start. So you'll see that we have a lot of different properties in here, a lot of different things that we're working with. It's just how we're going to work with them is very important to us. You might notice I am using the IO stream up here, but there's no header. Excuse me, there's no like output stream. I'm also using namespace standard. Notice that if IOStream goes away, my string objects go away. I can put in, oops. Notice that if I put in string, it doesn't even find it here. So that's the reason for having IOStream. Oh, come on. Oh, sorry. Okay, I can't put in string. IOStream probably is including the stream, which is why that was there. So I just kind of went a little bit generic with it. It's no big deal. As far as that goes. So if you're kind of wondering about that, if I don't have that stream or string or anything like that, then my string, which remember is a class inside of C++, wouldn't show, and that would be a problem. Okay. Any questions on setting up that base class and why we have something that has a little bit more information about it, because it's going to be used, in ways that I may not be able to contemplate. That's a big part of the reason why it gets used like that. Other example, in a great example I've used before, I think I used this when we had a Python class together, was talking about a dice. If I've got a dice, I might be thinking, oh, I've got a 6-sided dice, and it can roll between a 1 and a 6. And that's great if I'm writing like a Yahtzee game, or I'm writing a lot of different dice type of games. However, that's not the only type of dice. So with object-oriented programming, I need to think more about all my different potential applications I'm going to be using it for. And if I'm going to go with the drive class, if I create a base class or a parent class that I know is going to be derived, I need to think about how can I create a class that others will be able to use, give them the most flexibility and power with the minimum amount of work that they have to use. At the same time, and this is kind of a dilemma, is I don't want to make this so complete that it becomes too much overhead because 90% of it's not necessary. And this is the biggest problem that you have when you start working with object-oriented programming, is how much information is really needed. So always have that kind of run in the back of your head. How is this working? How am I going to do this? What am I going to do, etc. Think about stuff like that. It will make your life a lot easier going forward. It won't solve every problem, but if the more problems you can solve early on in your what we refer to as design stage, the better it's going to be. And the big part of that is because the earlier you find a problem, the less technical debt that you have to deal with. And that is the less places where you have problems that you have to go and continually work on trying to solve and fix. It's just out there for you. So that's a big part of why you want to really think about this. In future classes, we talk about technical debt. We talk about the design phase and modeling phases and stuff like that, where all this is taken care of. It's in a software engineering course that I also happen to teach. We'll also be looking at when we start really delving into object-oriented programming in a lot more detail, especially with languages that have this built in from the idea of object-oriented programming is built in from the very beginning. We'll talk about some additional features that are going to be available to us, things that are either a little bit more challenging to do in C++ or are not able to be done in C++ because that wasn't built essentially from the ground up with it in mind. The reason why it's not in C++ is, remember, C++ is an extension of C, and it is therefore we have in a lot of ways the technical debt of C. Well, why do we have technical debt from C? Well, it was done as a procedural language. It was written 45, 50 years ago at this point. And computers were not as powerful. Computers didn't have the functionality. So we have to keep that in mind. Any questions on that before I go into the next little section real quick? If you don't have any questions, just kind of do the thumbs up or hand raise type thing. I think it's a thumbs up. Yeah, there we go. Awesome. Okay. So the last thing I want to talk about, I wasn't sure if I was going to talk about today, if I was going to talk about it on Thursday, but since we have time today, we got done a little bit earlier than I was expecting. That's okay. I want to talk about today. That will give us more time to work on projects and stuff on Thursday. The thing I wanted to discuss was when and why do you use different languages? You know, there's a lot of different computer languages out there. Why do you pick language X over language Y? And why would we learn something like this? This is C++ is definitely one of the more complicated languages to learn. By no means is it the most complicated. There are languages that are, I think, intentionally designed to be complicated. There's a computer language out there, I cannot remember what it's called off the top of my head. The entire thing is based off of symbols. So, like, instead of typing in like int, you type in an open parenthesis or something kind of weird like that. That's intentionally complicated. I'm not talking about a language like that. But C and C++ especially, both of those require that you do a lot more hands-on with the managing memory and things like that. So why would we still use these languages? And these are very active languages. You can, if you go on to someplace like Dice or Hot Jobs, something like that, you can find people who are needing C++ developers. So why haven't they moved to easier languages? And the core component always falls into two categories. One is, what was the language originally designed for? Knowing what the language is designed for becomes very important to understanding how did it go about trying to solve that problem. If you look at, for example, PHP, PHP, a lot of people have a love-hate relationship with it. They either love it or they hate it. And a lot of it goes back to its technical debt, where it was built off of another language called Perl. And Perl was designed as a file and stream manipulator. That's really what it's designed for doing, was manipulating files. And when someone said, "Oh, I need to build a web page," you know, a web, essentially a web processor, I need to be manipulating some files. I'll just use Perl because I know Perl. And so it does some of that stuff really, really well, because the idea of taking one file and manipulating it and sending it to an output stream across a network called the internet to be viewed by your web browser makes it very effective for that. On the other hand, it's got some weird idiosyncrasies built into it as well. But some of that goes, like I said, way back to the fact of where it came from and what its origins were. C++ is derived from C, and it's got some of those weird origin things. But C was designed for writing systems level applications. Stuff that ran behind the scenes, wasn't designed to have a lot of fancy interface stuff. And speed is very, very important. Speed and memory size. We don't want a background application that's taking up 2 gigabytes of space. So C and C++ became used for a lot of those background tasks. They're used a lot in your operating systems. In fact, most operating systems are actually written in C because it's about 10% faster than C++. And let's face it, a slow operating system, even when it's only 10% slower, is a drastic change, and people will, their impression of it will be affected negatively. So a lot of your operating systems are still written in C because object-oriented does slow you down a little bit. Now, with a 10% slowdown with modern computers, that's usually not enough. And so a lot of your system application type of things, backup software, those types of things, maybe antiviruses, those should all be written in C++. They still need to be fast, they still need to be very efficient, and we're willing to make the trade-offs between complexity and speed. More complex for the developer, much faster runtime for everyone who winds up using it, and hopefully that's lots and lots and lots of people.
I have a question. Why haven't
Yes.
they, with modern, why haven't any modern languages managed to be even more efficient or faster or whatever than C in these
Okay.
older languages?
Great question. And so the reason why is the trade-off becomes into the where do we want to spend time? And do we want to spend time in development of software or when the software runs? So if I were to take two seemingly identical type of applications, one written in C and one written in C sharp. Okay, C sharp has come out after C++. It has quote unquote solved a lot of the complexities that are involved with C, especially with the memory management, deal with pointers and things like that. It is much faster to write a C sharp application because of that. If I took two equivalent, for lack of a better term, two equivalent programmers and gave them a task, the C sharp developer should have that written first. Because they don't have as much debugging they have to do to figure out, memory errors where stuff gets lost. They don't have to worry about, running out of this type of memory space because the C sharp runtime that kind of runs along with it in background is going to handle all that for them. The C++ developer has to be very cognizant of that. And so it may take longer to run. It may take 30% longer or 50% longer. What doesn't happen, and I want to make sure you don't think of it this way, is if I say x equals x plus 1 in C++, and I say in C sharp, those things are going to take about the same amount of time. Where it gets more complicated is if I have to make additional function calls because I'm going out to an object and my class is protecting my data. Well, if I were to write a function in functional C, so where I didn't have objects to go store that information, I could just go quickly and grab it directly. I'm not having to make those extra function calls. That speeds me up. In C sharp or in Java, where I'm an object-oriented language, I have to make those function calls. It's going to slow it down. It's going to be handling the memory for creating those objects. And because I've got objects that every method inside of an object has to be recreated. So instead of like in a functional C where I have one function that sits out there, every object has to have its own copy of the function, so it takes up more memory. It does that to protect all those private properties inside of my objects. So I've got to have extra memory. I've got to have now memory managers to handle that and move stuff around behind the scenes. I have extra function calls to be done. That's why it's slower. It's not that the actual line by line is slower. It's that all these other things are going on are more steps behind the scenes that make it slower. So does that matter to the end user? And that's where the big question comes in, because I might say, you know what, I've got to pay this developer $50,000 a year, $70,000 a year, $100,000 a year. That's a big cost for me. So if it's 10% slower, but the average user isn't going to care about that, you go and use a modern language. Python is a wonderful example of this. Python is really quick and easy to just bang something out of a simple to moderate complexity. You can start getting really complex. You're not using Python. I'm just going to let you know. In most cases, the trade-off is that it's slower because it has to be interpreted. It has to be, every time it runs, it has to go figure out, okay, what am I going to do? Let me convert this to machine code. Okay, let me go run this. The advantage is that I don't have to write a Mac version. I don't have to write a PC version. I don't have to write a Linux version. I write a Python version, and I take the performance hit because I'm not writing versions specifically for 3 different computers. I don't have to have 3 different developers working on the same project. So the question is, am I willing to pay a trade-off in a slower application for a faster development time? And if the development time is more important, I'll pick a slower language. If, however, let's take, for example, an antivirus software, and let's say it took 30 seconds every time you went to access a file for it to scan your file to see if it has a virus before you accessed it. How frustrating would that be to you as a user? I'm betting that that would get really frustrating really quickly. I just need to open up a file and boom, 30 seconds, I gotta wait. And that doesn't count the time that it takes to read the file and process it and then display it. And so now the time, the penalty and time to run it becomes more painful. And I say, well, I need to write it in a more efficient manner. More efficient computer runtime wise usually is going to mean more work on the developer side. And whether that means that we have to write specific memory managers to handle all of our pointers and stuff like that, but I can fine tune them and get them running very, very quick versus a very generic method that runs for everyone. And that's the key thing is, am I running for everyone or am I running for this specific instance? And that's one of the things that we have to kind of keep in mind whenever we're going through a process like this. As languages have evolved over time, and in fact, Microsoft just announced the .NET 5 version 5 of .NET. I remember when .NET 1 came out, that was probably, oh goodness, 15 plus years ago now. I remember sitting in a big conference room when they were announcing it. And it did some really good things. Version 5 is going to add new features. It's going to say, well, I haven't looked at it yet, but I'm going to make some basic assumptions that .NET 5 is going to add more features. It's going to require more RAM to run. Why? Well, you're getting all these extra features built into it. So it's going to make your development time for your developer to go down. Why? They don't have to write it. It's built into this. The flip side is you're going to have more RAM on your end user's computer. So instead of being able to say that you only need 2 gigabytes of RAM to run, you're going to have 4 gigabytes of RAM to run. Or instead of 4, you're going to need 6 with 8 recommended, or whatever that value is going to be. Most applications, as the languages have evolved over time, they try to sometimes do things to make them more efficient, or give the options of making things more efficient. If you remember correctly, when we looked at project properties, and give you just another kind of example of this, we come in here and we go to platform here. The platform is set for Win32, but I could make it x64, which is 64-bit. I can go into some other options under some of the other things that we do and work on configuring things and making it more efficient for a specific processor. So I can say, this is really designed specifically for like an AMD processor, and I'm going to take the AMD specific improvements. So I can do, they've allowed us over years to add improvements so we can take advantage of certain hardware improvements, of certain chip design manufacturing between 32-bit and 64-bit. So they are making things faster and better where they can. But you're never able to keep up with something that is specifically designed for at low instance. If you take that to the most extreme end, you find development with like what my father used to do. My father worked on integrated applications, and he was writing with very simple chipsets for the most part, but he wrote in something called assembly code. And what might take me to write using C++ or Java or something like that, a couple of pages of code, might literally take him hundreds of pages of code. But he was looking at, instead of a generic for loop, he would write a series of statements, and it might be a dozen statements to do the same thing, that went into the specific hardware level machine code to do that exact same thing. So why would he do that? Well, a lot of times his programs were running where, when I would write something at the same time when he was developing, I might write something that be 100 or 200 kilobytes to do. He could write a similar type function and use only 8 kilobytes of RAM. So there was a huge trade-off performance, and on an integrated processor, integrated circuit, or control board, that's not uncommon. You don't find megabytes and gigabytes of RAM. I think before he retired, 64 kilobytes of RAM was as much as he ever went to, and he thought that was just an insane amount. But he was measuring, where I measure my code a lot of times in performance on the tenths of a second, he would measure his code in running on milliseconds. So instead of a 0.1, he'd be 0.001, and he would be writing code that would be that efficient, that fast. And so there's always that trade-off. The amount of work he had to do to get that type of speed was just unbelievable. You can't write something generic enough to run on all these different computers with that type of with our level of generality to get his level of speed. And so that's why you have that trade-off. And even when they do things to, like, for example, allow us to define a platform, and if you dig into it, you can specify specific chipsets and stuff like that, it's just not the same. There's always a level of because that abstraction, there's going to be a level that's going to pull us back. And nowadays, you guys don't think about 3 gigabytes processors. Speed is if I'm 10% slower, I got a 3 gigahertz processor. It's not that big a deal. Um, when I started working, my first programs were written on a computer that was a 4 megahertz. Um, so literally 1,000th the speed of what the modern computer is that you get. Um, so that's why we're using stuff that's not as efficient, because hardware has made it so where the developer time is the more expensive component. So let's do things simple, a little simpler and easier. And we'll look at in CIS 210, we'll probably be looking at Java a little bit more specifically. And in 460 intro to algorithms, I've been doing almost everything I think has been done in C#. And part of it's simplicity. Just all honesty, it's just this is how we can do this and be simplistic, and that gives you the ability of, well, I want to look at doing system level stuff. I'm using C. I want to do something where it's very fast. If I'm doing like a real-time game, most real-time games are written in C++. They don't have to be as fast and use C nowadays, so they use C++, and it still makes it so it's extremely fast. But I have the trade-off of it's more complicated, which is why development for a game is 18 to 36 months, not 6 months. Now, if I'm doing a strategy game, I can go simpler. I can use Java or C# or something like that. So it's a lot of it is dealing with how fast do I need to do, and it's not because they put like little wait timers in there. It's because of how we access data and move stuff around inside of memory and have to use function calls to go get stuff that might be more readily available in other methodologies. So I hope that answered that question. It's a long and winding question, but that's what seems like a really simple question is actually very involved in the whole process. So very good question, but it's not as simple as it sounds just initially. Okay. Any other questions with that? Just kind of why would I pick one thing over another? And while you might be thinking of that, just real quick, know that there are also languages, and I've seen people that they will write a proof of concept in something like Python, which is relatively simple and easy to knock something out in, but they did that trade-off, and then they went in and they rewrote it. Once they proved that it worked, once they proved that people wanted it, they might write in something else so it's more efficient later on. So that was always a possibility as well. All right, well, if there's no other questions, I think we'll call it a day for now. We'll look at how we're going to derive classes from this generic geometric class on Thursday. That's going to be what we're going to do. Just so as kind of like an FYI. If you have any questions, don't forget that tomorrow I have office hours. If for some reason you are unable to come to office hours, and we've had a lot of people who I know are being called into work for various reasons, or they're out volunteering and helping because of the virus and stuff. They're taking food to people who shouldn't be going out, like the elderly and stuff like that. If you can't make it, I do understand. Let me know if there's another day or time that works better for you. I'll try to work around that schedule as long as I don't have other classes that are meeting. So do keep that in mind if you would. Don't feel like, oh, I can't come to the class because of XYZ. Just give me enough heads up, a couple days heads up, so I can rearrange things as necessary. Otherwise, you all stay safe. I look forward to seeing you on Thursday, if not before.